Hello, it's Keith here, and this is lesson 62 of the platform-specific series of my 650 assembly programming tutorials. We're looking at my so-called Mintile this week. This is the multi-platform tilemap code. We're looking at it on the VIC-20. Now, Mintile is designed for bitmap graphics, and it works with a hardware tilemap on the systems that are capable of that. However, the VIC-20 is only capable of text-based graphics and the character block graphics that could be argued to be a very low-resolution bitmap, just depending on how you look at things. But for fun and just to prove the point that this is multi-platform, I've ported the Mintile code to this system. Now, that rather confusing blob on the screen is the Chibico character. It looked a lot better on other systems, but that's all we can do on this one. And like on the other systems, the tilemap can scroll and the character can flip from left to right. Mintile supports X-flip, but it doesn't support Y-flip. The reason being, Mintile was designed for a game that only required X-flip. I'm working on a successor called Maxtile, which I may port to this system. I haven't decided yet. That supports X and Y flip. It also supports a lot more advanced things, which none of which are going to be really possible on a character block based system, but I might give it a go just for proof of concept kind of thing. Now, if you want to create graphics for the VIC-20, you can use Sprite editor. That's what I used. So Sprite editor is my free Sprite editor. It's open source. You can download the source code and mess with it if you want to make it better. And we've got this option here. We can use this 2x2 character block here, and that will convert our graphics to a character block representation as best as it can. So that might be what you want to use if you want to convert your graphics to horrible blobby things like this. But as I say, it's really just a proof of concept here, and I thought it was interesting to see how we can make a very graphically limited system do the same kind of things as we were trying to do on systems that are very powerful. So, okay, let's go over to the code and let's take a peek. So this is the code. As always, we're only going to look at the graphical platform-specific code. We're not going to look at the, the bits of the code that are doing the general initialization and the moving around of the object, because that's all just, reading in values into zero page and so on and so forth, which you should know. We're only looking at the graphical stuff. We've got our screen initialization routine here, which is loading in the VIC screen settings and transferring them to the hardware here. That's just setting up the screen. You can see those settings here, and if you want to change any of those, you can go ahead and do so. Now, on the VIC-20, we actually have the potential to set colors. However, the way that Mintile works, it doesn't actually have a color attribute for these tiles. That's something that hasn't been done at this stage. So what we're doing here is we're just filling the entire color RAM with a single color here. So we're using color 3 here. If you want to change the color, use a different one, you're welcome to do so. And then the rest of the routines here, this is initialization for the test tilemap and the test graphics. So that's not what we're going to be looking at today. Now, the way Mintile works is it actually breaks up the object it's trying to draw into individual strips. Now, there's two kinds of object. There's the entire tilemap, which is the full screen, and then there's the so-called sprites, which are the small movable objects. And either way, they're split up into strips, and we start from the left, draw to the right, move down, and keep doing that until the object is built. So the multi-platform code, which is covered in a separate tutorial series, there's a whole series on the multi-platform Mintile code, but the only platform-specific parts are the parts relating to that job of drawing the lines on the screen. Now, if we're drawing the entire screen, then we just start from the top left-hand corner, and the way the screen memory is set up here, we start drawing from memory address 1E00, and that will draw from the top corner of the screen. But if we're drawing a sprite, that could start in any position at all. So we have this getScreenPos function to calculate the VRAM destination based on an X and Y coordinate in the 0-page entries B and C. Now, the coordinates are in what I call logical units, and that means pairs of pixels in most cases. So one logical unit is 2 pixels, but with this system, we don't really have pixels, we just have character blocks. And so, to transfer the compatible code along from the other systems, one tile, one character block, is 4 logical units in both directions. And so you'll see there's this kind of division of the X and Y coordinates by 4 to get the logical units. Now, what we're doing here, because of the rather strange VIC-20 screen size, the screen is basically 22 tiles across, 22 character blocks across. And so what we're doing here is we are converting the coordinate in logical units of the x-axis here and storing that in L. Then we're taking the y-axis here, converting it to a number of tiles here. And then we've got a loop where we're basically repeatedly adding 22 to the memory address here and storing that memory address and then returning it. Now that's not necessarily the most efficient way of working this out, but 22 is a bit of an odd number, and to be honest, the VIC-20's tiny screen size, limited graphics, processing power is the least of the problems. So this is not the most efficient way possibly of doing it, but it is perfectly sufficient for today's requirements. Now, as I say, when we're drawing an object to the screen, we have a do strip routine. And so what we've got here is a routine that's compatible with the other systems. And so we're loading in a tile number from our source tile map in 0-page entry BC. That's a 16-bit entry BCS there. That's made of a BS and CS. It's a 16-bit pair. Now, our tile maps come in two forms. There's the background tile map, which is this thing here. And then there's our Sprite tile map, which is the tile map for the miniature object. And these will select tile patterns from our tile pattern data, which on most systems would be bitmap data. However, on this system, it's actually character block numbers, basically. So these are character block numbers. You could type in ABC here and use those as the background if you so wish. Well, in fact, we have, but we've inverted them. Anyway, as I say, this is the actual character block data that we're using for our patterns. And this is compatible with the other versions which would use bitmap data, but as I say, it doesn't necessarily make sense from a optimal way of working with this system point of view, but it does make sense in a multi-platform way of allowing code to be ported between systems point of view. So we're loading in our tile number here from our source tile map. Now, if it's a 0, that has a special purpose. The background is actually a cache of changes. We only use a single buffer, screen buffer, so the changes are drawn to the screen and then marked as done, so we don't try and draw those tiles again. However, for the sprites, we don't want to do that, and a 0 in there will actually be a transparent part. You can see around the so-called feet of our character there were a few tiles that are unused, and that is the 0 tiles for the sprite. So we're loading in the tile number, and if it's 0, we're going to skip over this part of the code. If it's not 0, we then decide what to do based on the tile clear flag. If the tile clear flag is set, then we're going to clear this tile, write it to 0. We would do that for the background. We wouldn't do it for the sprites though, so we need to change that accordingly. Okay, so we've got our tile number, but that isn't a direct character block that we want to draw to the screen. So we look up the character block within our so-called pattern data, which would be bitmap data on the other systems, but on this one it's character blocks, a list of character blocks, and so that's the DES pair there. That's the 16-bit address DES in the 0 page. So we're looking that up based on the tile number we selected here. And we then simply write that to the screen. That's the final character block we're drawing to the screen if we're not flipping the tiles. What we then do is we increment our source source tile map address here, so we're reading in from a different tile next time. We're then incrementing our HL destination, the VM destination, moving it across the screen for the next tile. IWhale is our tile count, and we're repeating until we've drawn all the tiles in this strip to the screen. And then once we've done that, we return. The calling routine will call us back for another strip if one is required. So that's how we're doing our unflipped images. Now, how about the XFlip versions? Well, one option on this system would be to have literally a second set of tile maps that could be used for the sprites that are flipped. But again, we're working in a compatible way that mimics the way the other systems do it. And so what I've done is I've created a lookup table of equivalent flipped characters based on one character is a X-flipped equivalent of another. So for example, here we've got the left and right less than and greater than symbols there, and those two are horizontally flipped equivalents, so we're storing those there. And we've got various versions here of character blocks we might want to flip, and then we've got the actual blocks, the block graphics that are used, this kind of thing here, and we've got the various versions here and their equivalent flipped versions. Now each one only appears once, so if either of this pair is found to be the character we're about to draw to the screen, we use the opposite one. So we would convert less than to greater than, or greater than to less than, and so on. And so that's how we are going to use this lookup table to flip our source data. So we've only got one source tile map. The lookup table will convert that as required. Okay, so we're loading that lookup table into the BC pair here. We're loading in our tile that we want to show to the screen as before, and we're doing the same clearing as before. That's all the same as last time. Now, what we're doing here is we're loading in the pattern from the pattern data in DES here. That's from our pattern list there. And then we're storing that in HS, and we're going to use that when compared to our lookup. So Y is going to be the offset in our lookup that we're considering. we're loading in the lookup that we might want to compare to. And if that's 0, we've actually reached the end of the list. And so in that case, we're going to just jump down to here, and we're actually going to show the original tile pattern back to the screen. So we haven't managed to flip it. Maybe it's a letter P or something, who knows. We haven't managed to flip it, so we'll just draw it the same as it was before unflipped. It will be in the flipped position, but the actual character block will not be changed. So that's what we're doing in the case that we've got to the end of the list marked by a 0. In all of the cases though, what we're going to do is we're going to compare that first value that we read in from the list and see if that matches the character we want to flip. If it does, we want to use the character afterwards as the equivalent flipped version. Now, if it doesn't match, we move to that character afterwards and we compare that. If this matches, we want to use the previous version. So that's what we will do. Now, if we want to use the previous version, we are loading that in there. If we want to use the next version, we're loading that in there. If neither match, we're jumping back to lookup again, which is up here, and we just keep reading in from that list. And so basically, we would be comparing to this. If it matched, we would return this, but if it doesn't match, we then compare to this. If it matches, we return this, and we keep going down that list until we get to the 0 here, which is the end of list marker. That's how this flipping lookup table works, and it works very well if within the limitations of character block graphics. Now, as I say, I'm not really seriously suggesting you probably want to use this code. This is more about a proof of concept in the way that even a very limited system like the VIC-20 can mimic the more advanced functionality of the other systems and allow us to port our code to some extent to this system. Now, I've done this kind of thing before with regards to, I did my Grime 6502 game, I did my YQuest game, I've ported other games to this system within the limitations of this system. So it's, as I say, it's definitely worth considering, doing something like this if you've got a game on another more advanced system and you want to try targeting this system. So anyway, as I always say, go to my website, you can download Sprite Editor, and you can download the source code for this as well, and use some bits of it if you can, or just maybe get some inspiration from it if you can't, because I say, with a limited system like this, if you're building from the ground up, you will build something far more specifically targeted to the capabilities. Anyway, thanks for watching today, and goodbye.